So I can tell you it's not much of a surprise. In fact, I don't know if my voice will even last until the end of this talk. Unfortunately, for some reason, my talks at the past few PyData events, when they've been put on the schedule, there's always been some problem or a title has been given to me. The last talk that I gave was at PyData London. It was called Python and Johnny Cash. I think this talk should be called Python and Tom Waits. Because my voice is really scratchy, no? Okay, next year I'll teach you who Tom Waits is. Anyway, another thing that I'm trying to do this year is I'm trying to give as many new talks as possible. So this is an interesting idea that I had for a project that I wanted to work on that could solve a common problem that I have when using a lot of data science libraries. Before I get started, as with all my talks, I'd just like to say we're at PyData Berlin. This is the third event. It's Saturday, May 21st, 2016. So let me describe the problem to you. But before I get into that, I just want to tell you what kind of problem this is. This is an engineering problem. And I really like this problem because unlike computer science problems or mathematics problems, engineering problems often have no one true answer. It's down to a lot of judgment, and it's down to what you think you can do to get some useful work done. There is no 100% correct answer or complete answer. There's actually no way to solve this problem completely, but there's a lot of work that we can do in order to make things better. There is no algorithm available. Trust me, the core problem here, which is that Python is impossible to statically analyze, is not something that we'll be able to solve. But there are some heuristics, and I want to show you one interesting heuristic. Also, another problem is, this is a new talk, so I only have a couple of results. I don't have a finished product, and so I'd love, if any of you are interested in trying to solve this problem, that you might come up and we could talk and see if there's some work that could be done to move this forward. So one thing is, I haven't solved this problem. There's only a couple of snippets of code that'll be provided when these slides go online. So let me describe the problem for you. I'm in my IPython notebook or my Jupyter notebook, and I'm writing a little bit of code. So I just use NumPy, and I create a linear space, and I just create a parabola. I have x and x squared. And I decide to plot it. And I know in matplotlib I have my .pyplot sublibrary, and I have this plot function, and I plot it. But I want to change this plot a little bit. I want the plot to be in green instead of blue. And I kind of know that I can pass this third parameter, g, as a string, and that works. And maybe instead of a line, I want it to have plus as the markers. But as I get more and more into this, and I want to do more with my graph, I need to figure out, well, what does this plot function actually support? So I look at the help text for the plot function. And this is why I call it the Kwargh problem. Whenever you see the help text and it says Kwarghs, you go, Kwargh, because you can't really figure out what this function takes. Now the matplotlib developers here have been kind of good, and they've worked against their own interests because they have hard-coded into the docstring what some of the Kwarghs are and where the Kwarghs come from. And they've added a dependency that they have to maintain for our benefit. But you can see the Kwarghs could be all of these things. And yet, they don't tell us what the arguments are in the signature itself. This turns out to be a very common problem, because maybe I'm doing something in pandas. I create a data frame, and I call .plot on that data frame, and it doesn't quite do what I expect, so I look at the help text, and I see more args and kwargs. And in the case of pandas, you can see the kwargs right here. It doesn't really tell me what those kwargs could be or where they come from. I know they're being passed onto libraries down the chain because both this matplotlib.pyplot.plot is a convenience function, and pandas is full of these convenience functions. And they're being passed to core libraries that matplotlib, or parts of matplotlib in the case of matplotlib, or core libraries in the case of pandas, that are actually consuming these arguments. So let's try and analyze very, very simplistically where this problem is and how deep this problem goes. So I'll just use the inspect module to write a very simple function that will just tell me, given a function, I'll grab its signature, and I'll see does that signature take ** keyword args. And then I'll write a really simple little lambda that I'll just go through a module and find all the callables in that module. And I'll just take the average of those. So I'll see what's the average number of callables exposed by this module that has the ** keyword args. And I'll run it over a couple of simple packages that I have installed in my unmodified Anaconda 3. So you can see for pandas, over 40% of the things that are available, the callables, by this very rough metric, the callables that are available to you when you import pandas as PD and you do PD dot whatever, almost over 40% of them have keyword arguments. In the case of Matplotlib, it's actually not that bad, only 10%. In the case of SymPy, surprisingly, a lot of SymPy, which I don't use that much, takes keyword arguments. And you can see in the case of some other libraries, like NumPy and sklearn and Bokeh, there's almost no usage of keyword arguments. So you might expect that if you're looking at the help text for something like sklearn or Bokeh, that help text might be a lot more helpful. You might have better autocomplete. You might be able to understand what arguments are passed in because it doesn't have this ambiguating keyword argument problem. Whereas my situation when I use pandas and Matplotlib is all the time. I'm trying to figure out what arguments does this function take because I want to slightly modify what this function does. In the case of a plot, I want to slightly modify how that plot looks. And I can't figure out what's the magic combination of parameters I need to pass so that one parameter passed into .plot gets passed to the marker object to create custom markers that look a special way. So let's try and understand why this problem exists. Because an easy thing that we could tell the library authors is just stop using keyword arguments. It's a great part of the language, but don't use it. And of course, that's a bad thing to say. I mean, keyword arguments are a great part of the language, and you'll see why that is. If we look at the libraries that have this keyword argument problem, they're mostly libraries that provide us a lot of conveniences. What happens is, when you're writing a core library that fulfills some fundamental task, then you probably know what arguments a function takes. But when you're adding convenience on top, you want to wrap those core libraries, those core pieces of functionality, but you don't want to create a dependency between the convenience layer and the actual code that it's wrapping. If you were to create that dependency, then every single time something in Matplotlib changes, the pandas authors would have to change the arguments that their functions take. But they don't care about what arguments are being passed down the line to Matplotlib. So instead, what they want to do is they just want to very lightly wrap the underlying functionality, give you a slightly nicer interface to it, but not block you from doing anything with the core library that you could do if you were using it directly. So in the case of pandas is a fantastic case of this, because think about how much you use NumPy or Matplotlib without actually ever explicitly importing NumPy or Matplotlib in your code. You do it all through some convenience layer provided by pandas. And the pandas authors do not want to manage the documentation burden or the code burden of having to change the arguments that are passed to these convenience methods every single time the underlying libraries change. So it's necessary that we allow authors to use these keyword arguments. The question is, how can we improve the documentation so that we don't have the case with Matplotlib where you have to have somebody statically managing a doc string and where the arguments are going, and where you can provide a little bit more information to the user. Now, there are a couple of guidelines for how we go about solving this problem. Our task here is to pierce this Kwargh veil. We have a function and we don't know what gets passed into it. We don't know what keyword arguments gets passed into it. And we want to do our best to pierce that veil. We want to figure out at least a couple of them. We may miss some of the keyword arguments. As long as we don't get it completely wrong, we're actually doing a little bit better. You might think that if your autocomplete gives you a couple more suggestions than it did otherwise, that might be an improvement. And so you can see why I call this an engineering problem. One interesting thing about this problem is because the goal is to supplement the documentation, it frees us to use some very obscure techniques. Because a lot of techniques that we wouldn't use in building the libraries themselves, we could use in order to supplement the documentation, because the actual deliverable here is a fairly static product that doesn't change that much. It changes per release of the code. And so you could add this as some additional pass whenever you do check-ins or as part of your continuous integration process. A great thing about this is we don't have to be 100% complete or correct. In fact, the information that we're providing to users now is very incomplete. So anything better than what we're providing now is, I think, an improvement. We can be incomplete. We can fail to say that an argument takes the specific Kwargh as long as you put a little star at the end and say, by the way, here are the Kwarghs that we can figure out are actually being passed in, and it may take some other ones that we couldn't determine. And that might be enough. And in some cases, like in the plot example, that might be enough to give people just a little bit more information to solve a couple more common problems. You could think that if you did that and then supplemented that with some human effort, you might get very close to having complete documentation and the ability to do correct, complete auto-completion in your IDE or your Jupyter notebook. Now, of course, at the same time, we want to be careful that we don't list a Kwargh as being an argument for a function that isn't actually an argument. So we can't be completely wrong, but we can be somewhat incomplete. Another thing is we might be able to focus on the simplest cases here. One thing that we'll see when we look at a static approach to solving this problem is that by its very nature, Python is impossible to statically analyze. And as a consequence, a malicious library author, like me, could construct situations in which there's no way that you could determine what arguments could be passed into that function without actually calling that function itself and waiting for it to throw a value error or some other exception. However, we're typically doing this in order to supplement our usage of common libraries that were written by common people, that were written to be usable, and so we can focus on much simpler cases than what we might expect from a pathological library author. So I want to give you two possible solutions to this, and I want to show you why one solution completely fails to work, even though it's probably the solution most people would think of, and I want to show you a somewhat obscure solution that I think might work if we could apply enough effort to it. So the first solution is static analysis. If this were something like C or C++, immediately you'd say, well, we just statically analyze the code base. And in a language like C, that might kind of work, but actually in C, that doesn't even really work. One static analysis tool, or one static analysis question that I ask C programmers and C++ programmers is, when you're in a file in a C or C++ program, and you see that it's calling function f, how do you find what source file that function f was defined in? And the only answer I've ever gotten was cscope or your IDE, because it's very difficult for you to determine what was included. I mean, you can track the includes, you can use your GCC-E and expand the includes, but you end up with a humongous mess, and it can be very difficult to figure out where that ended up. And that include is only going to tell you the signature of that function. It won't tell you the linkage. And so you may not actually know what the linkage is without looking at the build system. So even in C, it's very difficult to determine statically how a function is called or where a function comes from. And that's ignoring the situation with things like virtual functions and the dynamic features that you have available in C++. However, in Python, we might think that simple Python code might be amenable to static analysis. I will tell you this. Every time I've tried to use static analysis in Python, I found that it can be incredibly hard, even in fairly simple situations. There are some cases where static analysis works pretty well. So one case is, somebody asked me, we have this problem with imports in this very big system. We don't know what imports what, and we don't know the chain of dependencies for imports. It wasn't a problem with circular imports, because I don't think anyone in this room has probably run into a circular import problem in a while. But it was just an issue with they didn't know where the coupling in the code base was. And there's a static approach to solve this and a dynamic approach to solve this. The dynamic approach would be to write an import hook that logs every import, and so you could just run the system and see how the imports perform. The static approach would be to write a node visitor and just define all the import statements, and for the most part, in the majority of code, there's no use of path hooks, there's no use of import hooks, there's no use of the _ import function, there's no use of the import library. For the most part, if you see an import, it's either from blah, import something, and that's the form. And you can do that static analysis even without sophisticated tools like the AST library. You could do it just with grepping, just with regular expressions. So there are some cases where it works. In a case like this, in a code analysis case like this, it ends up being very difficult, and I want to show you why. Now note, I'm not going to tell you why it's impossible. Eval in Python makes it strictly impossible to do this kind of static analysis. But that's a very trivial thing to say, because honestly, the majority of code that we look at is not going to be some really weird eval code. There are some corner cases, there are some places in the standard library, such as the collections module, where eval or exec are used. Name tuple, which we're all familiar with, is one very common case where you see the use of dynamic code generation and dynamic code execution. But for the most part, it's still a fairly obscure technique in libraries. One thing that we might assume is that probably 99% or greater than 99% of the common libraries we're looking at, the data science libraries like matplotlib or pandas that we're looking at, are encoded in what you might call a non-dynamic space of expressions. What I mean by that is, actually I have a rant for why that's maybe a waste of Python, but the idea is that most of this code is written not too different than a C or a Java style. It's written fairly straightforward, just classes and functions calling other functions, and the composition is at the level of breaking things into functions and functions calling other functions. And many of the dynamic features of Python, monkey patching and overloading, are not really used. Now, you could say the code is written this way because it's intelligible to just any random contributor, and I think that's a really great reason to write code that way. You could say the code is written this way because it's pretty straightforward and we don't want to get too complicated. We don't want to overload ourselves with too much complexity for the sake of complexity if it doesn't solve the problem, and I think that's a great reason as well. But I will say that when I do see code bases that are written in a very Java style, I think it is a waste of Python. Because it turns out that these libraries inevitably reinvent dynamic mechanisms that are available in the language themselves. And very rarely do you see those dynamic mechanisms invented in order to get around limitations in the mechanism in Python. So for example, every large system I've seen invents its own configuration system, except the import mechanism and import hooks built into the Python language itself give you quite a bit of what you'd consider to need in a simple configuration system. You have the ability to define things in some format, a Python file. You have the ability to pull them into random parts of the program and have some global state for the configuration. That's the import module system as a global singleton, right? And you have the ability to add some code mechanisms and some overriding mechanisms. And you have all of that available in pure Python supplemented by just a little bit of mechanism around how imports work, namely import hooks. But if we were to do this stack analysis, how would we do it? We'd probably do it using the AST module, using a node visitor. So we'd identify the calls within a call graph, and we build it. And this turns out to be a fairly undocumented thing, but a pretty simple thing to do. So this is an example of a node visitor. This is a node visitor that it gets an AST and abstract syntax tree, and every time it sees a call, it just prints out that it saw a call. And it prints out what the function name was and what arguments it saw. And so here's an example of a function, and I'm going to run my AST node visitor on this, and you can see when I run it, it sees that there's a call to a function called G here and a function called H there. And you might say, well, this is actually pretty good, because if I used an approach like this on the pandas code base, I could create a call graph. I could say this function calls this function, calls this function, calls this function, and I could see what arguments are passed, and I could build a graph that says, this is the entry point and all the arguments that are passed in, and here how they get passed down the line to wherever they terminate, wherever the terminal function is that actually uses those arguments. And it turns out that there are only a couple of ways that we might consume these keyword arguments. We might pop them, we might subscript them. So we could figure out where a keyword argument, a star argument was actually used by just looking for all the .pops or all the subscripts of that variable name. One interesting thing is we can always see when something's passed on by keyword unpacking, because that itself will just show up in the AST. Here I'm giving you the names of the bytecodes. So if you do a bytecode analysis rather than AST analysis, you'd see these bytecodes. And you can also see where something terminates. You can easily see if the body of the function never uses any of the arguments, or where it uses the arguments, or where it doesn't call anything else. And you can also kind of see where a function may use unpacked arguments. But the problem is, even in fairly simple code bases, I suspect we'll quickly lose track of bindings. And I'll show you what that means. The easy binding that we'd expect is we have some function f that calls some other function g, and it just passes the keyword arguments down. And here we could see anything we pass into f gets passed into g, g takes arguments a, b, and c, therefore f takes arguments a, b, and c, our analysis is done. And that's a fairly simple analysis. And you might expect that a lot of code looks like this. But I suspect that especially in a library like matplotlib, and especially like in a library like pandas, you see something slightly different that makes this very difficult to statically analyze. Instead, you might see something like this, where you create some class, and then you pass those arguments to a method. And once you do this, we completely lose our ability to analyze which of these two methods we went down into. Because we have to know at runtime what this class was, and that could be determined by some other state, some other arguments, and suddenly the complexity of computation that we have to track in order to figure out which of these two paths down the tree we went explodes. I'd suspect that this is actually more the case than you'd think, and this shows up in some very simple cases. And so I would say probably static analysis in this vein won't lead you much of anywhere. Now, of course, it's possible for us to have unbounded complexity. I don't have a lot of time to go through all these examples, but I thought I'd come up with a couple of examples of just how complex an author could just naively make it difficult for you to statically track where an argument went by doing copies of the dictionary, by updating the dictionary, by doing assignments of the dictionary, and then you have to track state of the dictionary, by doing some really weird things to the dictionary, by using the operator module to pull things out of the dictionary. But it is true that we can always tell when you do a star keyword unpacking, even if you can't tell what got keyword unpacked. So it turns out that building this call graph statically is very difficult. One of the main problems is the AST has no knowledge of the symbol table, so you don't know the load context. You don't know if you see a name. You know there's a function by that name, and you could match it just nominally by seeing if there are other functions in that module with that name, but you can't figure out if it's being loaded globally, if it was locked into a closure. You have no idea. And there's, of course, as you saw on the last slide, many, many ways to obscure this information. So the other thought I had was, let's try doing this dynamically. If we were doing this dynamically, we'd have to have a test suite. And the big question that I'm not sure about is whether we could use gallery code or unit tests with sufficient coverage to actually cover all the places where arguments can be passed. I think that the matplotlib gallery is actually fairly complete in terms of all the different ways that you can pass arguments in. And I think that the coverage of the call graph that it would generate would be mostly complete, but I'm actually not sure. In the case of pandas, the unit tests might be more or less complete. Now, there's a question whether or not this could be included as a completeness metric for the unit tests or for the gallery. So how do we do that? Well, one simple way we could do this is we could just interrogate all the call functions. What I mean by this is, let me do this. If you look at the CPython source code, you can see everywhere where a bytecode for a call function, every time you call a function, every time you have parentheses, you call this bytecode here, and it ends up going into this function here, call function. And this is the central point for every time a function's called. So if you could interrogate this, either with something built into Python, like the line profiler, or just by patching your Python source code, you could see every single function call. And you could build a call graph. And if you had a representative suite of code that exercised all the code paths in your library, then you could actually get a good call graph. You can see that the majority of this problem is actually in building the call graph. But there are a couple questions about that. I don't know what the average depth of this would be. If the average depth is fairly shallow, this might be too much of a technique. I don't know how much branching there is. I think these would be very interesting metrics to track on these libraries. What's the average depth of how many calls go down before you actually hit the code that does the task that you want? Is it the case that pandas has many, many, many calls until it actually calls the code that does the work? Or is it actually fairly shallow? I'm not sure, and I don't have a gut feeling for this. How much branching is there? How much complexity is there in terms of one convenience function in pandas and how many possible things it could call? This could be a very meaningful metric because this could tell you how testable pandas is. Instead of being a test, it could give you a metric for this part of pandas is very difficult to test because it has so many modalities. And I also don't know how much noise there would be in these measurements. Now, I wanted to show you one cute thing because, it was a surprise talk and I was put up. So I'll show you one module that I presented a couple conferences ago, and I did a lightning talk at PyData London about. It's called rwatch, and it adds read watches to Python. So I'll show you how you could do this kind of analysis. I will say, before I show you the demo, this is a very weird patch. It's a very incomplete patch, but you can already get some kind of interesting results from it. One interesting thing, though, about this patch is, even though it's extremely obscure and extremely weird, remember, this is an engineering problem where our deliverable is better documentation, so it doesn't matter what technique we use. We can use some very obscure and very absurd techniques as long as we generate that documentation, because our users will never be exposed to those techniques. They'll only make use of whatever results we get. So, hey, how come nobody thought of this all day long? Oh, that's what I get claps for. Okay, so here's my rwatch module. You can pip install it. You import rwatch. And then in the sys module, you have get rwatch and set rwatch. If you look at the help text for get rwatch, it just tells you that it gives you the read watches, the targets for the read watches. If you look at it for set rwatch, it just says it's a mapping of object IDs to a function. What this means is you can create a callback. Oops. Format, object, frame, return object. We got to do that one more time. Okay. And then you can create an object. And then what you can do is you can say every time somebody looks at that object, call my callback. So I'll show you what that means. Every time somebody looks at the object X, it'll call the callback F. So you can see every time I trigger X here, it's calling that callback. So if I create a function G that takes some value Y and returns Y times 2, if I call G with X, you can see when I pass it into the function, it triggers a callback. Inside the function where it looks at it, it triggers a callback. Think what we could do is we could wrap at the entry point to our gallery code, we could wrap everything with these R watches, and then we could immediately see where they're used, how they get piped. We could build a data flow graph for how the data moves through all the functions in our library. So I'll show you a mocked-up example of that. Before I do that, I want to show you one really neat thing about this patch. Notice how in the callback I return the object. Oh, it's cut off a little bit. Oh well. There we go. Notice how I return the object. You can return anything from this. So look at this. I love this. Here's my callback. If the object is an integer, return the object times 2. Otherwise, return the object. Oops, from collections. And then what you do is you set an R watch, not on a specific object, but on every object. And if that object's an integer, you return it twice. So what this has, the consequence of this is, every number that you try and put into your system gets doubled, and it really, really confuses people. When you have x equals 2 and x times 2, what's x times 2 if x equals 2? 32. How about that? I love that. Isn't that great? Okay. So I'll show you. So one of the purposes of this talk is to show maybe a practical usage of something like RWatch, because clearly you'd never really want to do this unless you really, really, really hated your coworkers. So let's say that you have some code that looks like this. This is my simple module. It has a function called f, it calls g and it calls h. G takes an argument a, h takes an argument b. And I'd like to figure out that f actually takes either a or b, and I just threw away the rest, but you could think that here I just want to figure out that f actually takes a and b, even though I can't determine that from its signature. So I might have some test code that looks like this. Here's my library code, my test code, and it creates 3 objects, A, B, and C, and it just passes them to F. And what I can do is I can just annotate them like this. Instead of passing those 3 objects, I just set an R watch on all 3 of the objects. So I set that hook on A, B, and C, and then when I run this, whoops. And then when I run this, you can actually see, I wanted to test annotated. You can see that the R watch was able to statically determine what function and the line number where each of those arguments were looked at. So what you could think is, when I call my matplotlib.pyplot.plot, I could wrap all the things that I put into it. So I could go into the gallery code for matplotlib. At the entry point where it calls these functions, I just wrap all the arguments with my R watch, or I just wrap everything with my R watch, and then I immediately know the name of every variable and every function where it's looked at. And from that information, I could build a call graph, I could build a data graph, and I might be able to build a supplement to the documentation to say, the plot function actually takes these things, and they're used in this part of the code, and I could do that as an automatic generation step, which might be very useful. So that's the Kwargh problem. If you think this is an interesting problem to solve, I'd love to talk to you. You can tweet at me at Don't Use This Code. Thank you very much.
Thank you very much, James. I thought it was a nice surprise. Do we have any questions?
Thank you for the talk. I think this is a very annoying problem in the
well, by the way, who has this problem? Who's like, Kwargh? everybody, right?
But I was thinking about why not try to solve it from the documentation side, because normally when you look at the documentation of, for instance, dataframe.plot, you will see that the method called in matplotlib is mentioned specifically, right? Mm-hmm. So if there was some convention to annotate that in the documentation, you could like recursively build the documentation from top to bottom, right? And
so if you annotated what functions get called, I think the problem there is that that could fall out of date, and that's a lot more burden. I don't know that you'd be able to convince the library authors to do that. Also, if you want a joke answer, that sounds like work, and this is really just fun.
Well, but you're relying on that the libraries will be tested. They have tests, right?
So you're right. It might not be an unreasonable part of the documentation to say that this function calls these other functions, but the problem is that even in very simple cases, I suspect that you'd see that these convenience functions are creating objects and calling methods on those objects, and they wouldn't be able to even know. There's too much dynamism there, and they're using list-offs, or they're using substitutability, so that you could pass anything in. You could inject any dependency, so it may not even be knowable.
Do we have any other questions? Okay. Well, please thank James Powell again for a great talk.